Learning Goal 1.3, we're jumping right in with mass analysis and empirical formulas. So we need to remember that the empirical formula for a substance is the simplest ratio of atoms in that substance. In ionic compounds, the empirical formula is the formula that we use because ionic compounds do not have molecules, and so the simplest ratio is the most important ratio for those compounds. Molecular compounds might be some multiple of the empirical formula, so we take the empirical formula and multiply everything by the same number to get the molecular formula. But the most important and the information that can be derived from mass data is the empirical formula. The ratio of masses in a compound experimentally is determined from the total mass of the compound, and then separated into different elements so that we can find the mass of each element. That'll be presented in problems either as the mass percent, if it's already been converted from like the actual mass out of the total, so it could be the mass percent. It might be the mass, the actual mass, and the total mass is also given. And there might be actually missing information. Let's say your chemical has 3 elements. You might get the total mass and then the mass information of only 2 of those elements. So before you can do the calculations you need to, you would have to also find the mass of that 3rd element by just subtracting the 2 that you know from the total, and whatever's left over has to be the 3rd one. So if you're looking for the empirical formula from the mass information, there's really 2 steps to that. You want to divide the mass information, and it doesn't matter if it's the mass percent or the individual mass of each element. You want to divide that by the molar mass of that element to convert from grams into the proportions that we know are related to the atoms themselves, which is the moles. So we take the mass and divide by the molar mass, and we get moles of that element in the substance. Now, this technically is a ratio of atoms in the substance, but it's usually not a really nice and neat whole number ratio. So the second step is to convert that molar ratio into a whole number ratio simply by dividing by the smallest of those numbers. That sets that smallest number to 1, and everything else will round to the closest whole number. With some exceptions, if we get something like a 0.5, we might need to double everything. Or if we get something like a 0.333 or a 0.666, we might need to triple everything in order to get the correct molar ratios, because it isn't always true that the ratio is 1 to something. It might be 2 to 5 or 2 to 7 or something like that. It might be 3 to 7, right? So we may have to, if it doesn't come out to very close to a whole number, we may need to multiply everything. So there could be an optional step 3 if we get one of those readily identifiable fractions, such as 0.5 or 0.333, 0.666. The other thing we might need to do is, if we're given empirical formula information, we might need to calculate the mass percent of a substance in that formula. And that could be for multiple reasons of data analysis, measuring the purity of a substance, or so on and so forth. So we might need to know that mass percent information. Maybe we want to use it in a dimensional analysis problem. So we do that by almost the reverse steps in a way. We're going to take the ratio from the empirical formula and multiply it by the molar mass, converting from mole ratios to mass ratios. Then we take that mass and find the total mass of the molecule and or formula, and take the partial mass of the element and divide it by the formula mass. This division of the part out of the whole gives us a percent. So the percent by mass can be calculated from the empirical formula, essentially using the reverse steps. First, multiply by the molar mass and then divide by the total formula mass to find the percentage. Let's get this information into your study guide and then we'll practice some problems. Here's your first AP example. Pause the video and try this problem. When you're done, push play to see how you did. This problem is asking for a simplest formula, but instead of giving our data in grams or percent, it's actually already given in moles. So the first step of finding the simple formula is done. So instead, we'll just start with each of these elements and the moles of each and perform step 2, which is to divide each of the numbers by the smallest number. Once we do that, we should have our molar ratio. Since this is a multiple choice question and we can't use a calculator on the multiple choice questions, thankfully these numbers are pretty straightforward and we could use some mental math to see that this is a 2 to 1 to 3 ratio, which is shown in choice C, 2 to 1 to 3. Let's try another one. This one is given by percent rather than by mole. So you'll need your periodic table. Pause the video, try the problem, and when you have an answer, push play to see if you're right. All right, so if we look up sulfur, we see that it has a mass of 32 and fluorine has a mass of 19. So we start with our percents, sulfur at 30 and fluorine at 70, and divide by these masses to get moles. However, these numbers are not perfectly able to do in our head. So I'm just going to say this is very close to 1, maybe a little less than 1. And 70 divided by 19, 19 is close to 20. So this should be a little more than 70 divided by 20, and that would be 3.5. So if I had to guess based on these estimates, it looks like C is the best answer. If we had a calculator and we did this problem, we would see that this is in fact the correct answer as well. So this is kind of a little warm-up of what you might have to do on the AP test when given problems that you might have to estimate and just choose the best answer that you can. Let's do another problem. This is an open-ended free response question, so you can use your calculator for this one. Pause the video and try this out. There's a couple of ways to approach this problem, and so we're going to start with a dimensional analysis approach where we start with what we're given, the 2.49 grams of the calcium sulfate hydrate salt, which just means that there's water mixed in with the salt as a solid. If we convert from grams to moles of the calcium sulfate hydrate, we would have to calculate the molar mass of the whole thing, including the water molecules. Once we did that, we could convert from moles of the hydrate to moles of water, perhaps. There's 2 waters per hydrate salt, and that's the stuff that's going to be evaporating. So if we figure out how much water will evaporate and use the molar mass of water, we could calculate the mass that would evaporate as a result of heating. Now, that's not what the question is asking for, though. It's asking for the solid that remains. So instead of converting to the water from the hydrate salt, we should instead convert to the calcium sulfate that's left behind. And so what we would do then is just use the molar mass of only the calcium sulfate. And this would allow us, through dimensional analysis, to get the mass that is remaining after heating. So we could do this problem this way. We would need to calculate the molar masses of both the hydrate and the calcium sulfate itself. So if we add up the mass of calcium and then also sulfur and 4 oxygens, we'll get the mass of the calcium sulfate, and we can put that into our dimensional analysis, 136 grams for that. And then we would have to add the mass of both water molecules as well, and that would give us the mass of our hydrate, and that turns out to be 172 grams. And so now we would just put this into our calculator and we would have our answer. However, I do want you to think about a way of doing this problem involving mass percent, where instead of going through everything, we instead immediately say, out of the calcium sulfate hydrate, what percent of that is just calcium sulfate? And so now we just would then say, well, that would be 136 grams out of the total 172 grams. And this tells us that 79% of the hydrate is due to just the calcium sulfate salt itself. So if we were to heat up the hydrate, we would expect that 79% of the mass would be remaining after that process. And so you can see that this is essentially the same thing that happens when we do the dimensional analysis. It's just perhaps a shorter way of getting to that answer. So 79% of 2.49 grams is 1.97 grams. And this is the same answer that we would get by using dimensional analysis. So the mass percent, which is the part of the total out of the total mass, can be used in this way to calculate this in just a slightly shorter methodology. That's it for this video. You're ready to move on to 1.4.